Thanks for having us. Thanks for giving us the opportunity to talk about our niche topic of hardware reverse engineering here in Italy. First time in Italy, at least for me. Hopefully not the last one. So yeah, let's get started. We're actually from Bochum, Germany. So we're working at the Max Planck Institute for Security and Privacy, which was founded 3 years ago. There is all other kinds of security research stuff in Bochum, like the university, the Security Institute, big pile of money called CASA, and a startup incubator called Q5. And as I said, we're actually working for Max Planck. So this is a rather new institute founded in 2019, which is supposed to grow to 200 researchers. I think we're at 70 to 80 right now. And one of its missions is to do interdisciplinary research. So that's it. And some acknowledgements for the work we're going to present. Like, we have an entire soccer team on our paper that we've submitted on the work, 11 people. These are some of them, some students, other PhD students, work colleagues, and other university and comedy people. All right. Some background, and I sadly have the obligation to do the dry part of the presentation, and Nils will do the fun part. So I will have to give you some background, because I think this is going to be a tough sell on you, like software people talking about hardware. I will need to introduce some basics, I guess. Some of you might have heard of field programmable gate arrays already, like FPGAs. It's a special kind of hardware, so it's not like your usual hardware chip that's manufactured and then fixed in functionality, but it allows you to actually change the implementation on hardware after manufacturing. So there is some configuration file called a bitstream that allows you to implement arbitrary logic on the device after it has been manufactured. And some of these FPGAs can actually be changed at runtime, so the implementation can be swapped at runtime, allowing for some fancy features. And this is a really simplified view of one of these FPGA architectures. How it basically works is that they have like reconfigurable logic blocks all over the place, and they are connected by some reconfigurable interconnect, and then there is some I/O, and all of this is configured by the bitstream. So there's bits in the bitstream controlling what the logic blocks implement and how the routing is implemented in the interconnect. These devices have lots of real-world applications, because usually they are used for low volume productions. So for example, if you want to do some testing in cars in the military, if like tanks or fighter jets are produced a couple of thousands of times, it doesn't make sense to produce an actual chip. In medical devices, in space, they are also quite big, and in total their market value is roughly like $10 billion. At least in 2020, and constantly rising. So they are kind of important. They have some advantages over ASICs. For example, as I already said, like the better cost efficiency in lower volumes, shorter design times, because you don't need to manufacture the chip. You can just program the chip. So you can like design your hardware implementation and go from there. And they allow for more flexibility, because you can actually reconfigure them. They have also some disadvantages. So for example, if you put them in things that you produce millions of times, they are really, really cost inefficient, because they are more expensive than producing dedicated chips. They require more area on the chip. They require more power to be run, and the computations are usually kind of slower than on regular ASICs. And this again is like the cost volume trade-off you have with ASICs and FPGAs. Okay, let's talk a bit about the bitstream. The bitstream is actually just a binary file, and the ones and zeros in that binary file directly translate to transistors, so to little switches on the FPGA that turn on and off different things. So there is a header, as with most files, and then there is a so-called sync word, and after that sync word, the entire, or the FPGA configuration starts. That is actually configuring the device, actually configuring the logic blocks and the interconnect. Okay. Netlist is another term that we might need to introduce. Netlist is basically just a circuit representation of what's implemented on the device. And usually if you hear about that, what you probably think about is, okay, it looks like this. So the netlist, there's some CPU, some AES, some communication, whatever, and you can clearly distinguish between them. Nope. Sadly, it usually looks like this. It's a huge mess of interconnected logic gates that do not make sense just by looking at them. And of course, like if you want to hardware reverse engineering, or why would you want to do hardware reverse engineering? there's different purposes. There's some legitimate ones, for example, for testing and detection of malicious manipulations. Usually hardware is not manufactured and designed at the same place. Some people design hardware, send it over to Asia where it's going to be manufactured, and then that's going to be sent back. So you want to probably detect manipulations if those happened. You want to prove IP infringement if other companies ripped off your IP, and you might want to do security analysis. But there's also illegitimate applications, for example, like the exact opposite of the legitimate ones, committing IP theft, design plagiarism, and, for example, finding insertion points for hardware Trojans. That can also be done using hardware reverse engineering. So, brief overview of what hardware reverse engineering actually entails. Again, differentiating between the ASICs, like the real chips manufactured, and the FPGAs that can just be configured. Starting with the real ones, you usually have the chip in the black package with the pins coming out. You first need to take off the package, so you need to get to the actual die that implements the logic. Once you have the die, that usually consists of different layers with the transistors at the bottom and then lots of interconnect layers on top. So sadly, you need to look at all the layers to actually understand what the chip is doing. So you need to do delayering, like grind down layer by layer and then take pictures of every layer. You need to process all these images, stitch them together, stack them so that you have a 3D model of the actual chip. And once you have done the image processing, you get out, like you receive the netlist. And then this is usually where we come in, like we do netlist and netlist analysis, because all the stuff up there that you see usually requires equipment in the millions, and we don't have that, and we don't know how to use it. So we usually expect the netlist to be there already. For FPGAs, it's a bit easier, because as I said, you just need that configuration file called a bitstream. So you need to get that configuration file of the FPGA or from wherever. And then you can try to understand the format of the bitstream, reverse engineer the bitstream format, and convert the bitstream to an actual netlist, because a bitstream is nothing but like a proprietary representation of the actual netlist. So if you find out what bit does what on the FPGA, you can actually translate it back into a netlist representation. All right, so most of you are probably familiar with software reverse engineering. So software reverse engineering has a quite active community, as you see here, in industry and academia, and there's lots of tools like GDRA and IDA Pro. They are advanced frameworks for binary analysis. They allow for plugins to be loaded into the actual frameworks. There's open source tools like GDRA again, but the situation for hardware reverse engineering is kind of different, because there is nothing out there. There is no tool that you could actually use for this netlist analysis part. So like 6 or 7 years ago, our group set out the challenge of developing one of these tools, because in the hardware world, if you want to do something, you need to do it yourself, usually. So that's when we started creating HEL, our netlist analysis framework written in modern C++, and it also allows for plugins and stuff. So nowadays we have this fancy software, and it doesn't crash as often as it used to back in the days. So we actually want to make some use out of it. So we set out and looked for targets, real-world targets that we could target, because we wanted to do some cool real-world case studies with all the work we have done so far. And that's how we ended up on Reddit, because if you don't know what to do, ask people on Reddit. And we actually posted on Reddit and asked for people whether they know devices that feature actual FPGAs that have cool purposes. Because usually, you've seen all the applications, military, space and stuff, it's hard to get these FPGAs out of a rocket, and it's hard to convince companies to give you those chips if you just tell them, yeah, I want to attack them. So we needed to find consumer products that feature FPGAs to actually target and reverse engineer them. First thing that came up is this Chinese intelligence asking. So after a while, after we actually told them our affiliation and stuff, we actually ended up with a good tip, the iPhone 7 and 7 Plus actually. They feature a lattice FPGA for whatever reason, because it's like a device sold in the millions, so FPGA in there makes no sense. But still, there was that one iPhone back in 2016, I guess, that featured the FPGA. So yeah, 2016. It's a lattice ICE40 Ultra FPGA, world's most powerful low-power FPGA. And of course, we asked ourselves, okay, why would you do that? Why would you put an FPGA in there? It costs like $3 to $4 per chip. If you manufacture ASICs in that quantity, especially those ASICs or an ASIC with that functionality, it would be in the lower cent. It would cost in the lower cent area. And ASICs therefore would be much cheaper. One note here, Apple refers to that chip internally as Maggie, and Maggie talks to Homer, which is another like ARM-based CPU. So they like The Simpsons, obviously. We are going to use the term Maggie throughout our talk at some points, but Maggie just refers to the FPGA chip and the implementation. All right. Then after getting that hint, we found some newspaper articles where people already wondered about what this chip might do. Some like suggested it would do encryption, others were more in favor of machine learning stuff and artificial intelligence. So that sounded interesting, target acquired, let's dive into Maggie's functionality. And just like a small spoiler, our work tries to tackle like three research questions. First of all, is hardware reverse engineering of a real-world FPGA implementation actually a realistic threat? Because no one has ever done that before publicly on that scale. What effort is required to do so, like to perform such a reverse engineering attack? And do we need to develop new approaches, or can we just take stuff from literature and execute what we have? Spoiler alert, we only discovered what makes the iPhone vibrate. There is no security implications here, apart from the IP theft thing. And this technique is going to be primarily about the techniques we use to perform the hardware reverse engineering, not so much about the outcome, because the outcome is some signal processing stuff, and I don't want to bore you with that. But the techniques are kind of cool. And this is for kind of structuring of the talk. In the paper we submitted, we split the entire process of hardware reverse engineering into 3 parts. First would be netlist recovery, so we have that bit stream, and we need to get to some high-level representation like the netlist. So phase 1 is netlist recovery. Phase 2 is kind of structuring the netlist, because a netlist is really just a big sea of gates with AND gates, flip-flops, OR gates, whatever, and they don't make any sense to you at all at this point. So you try to find like word-level structures, registers, whatever. And phase 3 would be the high-level understanding, so making sense out of all the like word-level structures, for example, that you discovered, and finding out what the chip is actually doing to, in this case, basically rip off the functionality. All right, let's start with phase 1, netlist recovery. First thing is you need to get the bit streams from somewhere. So usually, because FPGAs are, or at least these SRAM-based FPGAs, they cannot hold their bit stream permanently. So when you turn them off, the bit stream is like, it's flushed from the FPGA. It's not on the FPGA anymore. So they are stored externally. So there's different options. In this case, we were lucky. We are lucky that the bitstream is actually in the iPhone firmware. So whenever you download the iPhone firmware, the bitstream is going to be part of it. And it's in like an IPSW package, which is basically like a zip container. And there is a root folder in that firmware that contains all the firmwares for different components of the iPhone, including the bitstream. And you can actually see the bitstream down here in that container. And what we've seen, or once we looked at a couple of iOS versions, is that they actually, on the release of the iPhone 7, there was one version of the bitstream, and a couple of months later, I think about 3 months later, they actually updated the bitstream, which is one of the advantages of FPGAs. You can actually update them after the fact. So once you've shipped the iPhones, you can still change functionality in some way or fix bugs. And this is also one of the things we assumed here, that Apple was probably not ready to release this chip yet. And that's why they used an FPGA to be able to afterwards update the bugs they still have in their design, kind of. All right. Again, this allows for hardware changes via software updates, which is kind of cool. And how you would go, or if you want to reverse engineer the bitstream, there is some dedicated process that you would follow. So first of all, I mean, you need to understand the format of that bitstream. There's 2 ways to do that. You can either target the design tool that generated the bitstream and find like databases that do the bit mapping and stuff. But then it's hard to publish because you have like broken various license agreements. So we cannot really do that. And what is usually being done by some other open source projects as well is just to generate lots of bit streams and then try to find out what bit correlates to what functionality. In this case, you start with an empty bit stream, then you start instantiating some of the logic gates within your designs, and you just observe, after feeding it through the EDA tools, what changes in your bit stream, and then you build up a big database with all the correlations between the designs you've implemented and the bitstream bits that have been set. And this is usually how you get, or how you deduct the bitstream format through lots and lots of works, basically by fuzzers who fuzz the design tools with various, obvious different design variations. Okay, luckily we didn't really have to do this because someone else already did it. There is a project called Project iStorm out there, which is basically an open source bitstream documentation project. Their original goal is to facilitate open source design tools. So they want to be independent of the design tools of the hardware vendors, because you usually don't know what they are doing in the backend. You have no idea how to inspect whether they're actually properly working or whether they introduce any backdoors, any bugs or whatever. So they want to have independent open source tool flows for all of this. And of course, if you want to go from your hardware design to the bitstream, you need to understand the bitstream format to do exactly that, to open source or to create open source tooling. So we kind of abused their database, but the problem was that our exact FPGA was not really supported, but luckily it had a very similar architecture, so we didn't have to do lots of fuzzing again. It was all there for us, just some tweaks to the database, and we were ready to go. The big problem was that, as I said, it was not created for the bitstream to netlist part, not for the netlist recovery part. There was no tooling to convert our bitstream back to a netlist, so we had to adapt some existing tooling to actually do that. But there was also, not a piece of cake, but it was kind of easy compared to what followed. So what you would do here is you feed your bitstream into your bitstream conversion tool, of course, and out comes the netlist again. Netlist just being connected gates, interconnected gates. Okay, let's see whether this works. I've actually prepared, wonderful, small live demo of the actual netlist that we extracted. So now we've accomplished the netlist extraction. We have converted the bitstream to a netlist, and this is what it actually looks like in our tool. And as you can see, it's quite huge, and if you just look at it, there is no way to find out what's going on. So you really need to automate this process. Just let me. Okay. So within our tool, you have you see down here that you can get information of all kinds of stuff. There is the different net, the different gates. You can actually interact with the entire thing via Python. So we have Python bindings for most of our API. And you can do you can actually automate via Python scripts or also via C++ plugins. You can actually automate the entire reverse engineering flow. So our usual approach would be to look at stuff, find out whether there's patterns or anything interesting, and then automate detection for that kind of stuff. And as you've seen, this is kind of messy. So if you want to isolate, if you want to do some more useful exploration of the netlist, you can also just by unfolding it like this, for example, there's easier ways to actually achieve some understanding of the netlist, either manually or using automation. Anything I should add on the demo? No. Okay, wonderful. Then let's go back to the presentation. So phase one is basically completed. We have the netlist now, but now we need to do some pre-processing to actually detect structures that we can make sense of later on. Starting point is a netlist we've just seen. No labels, no hierarchy, no comments, no nothing, because it just comes out of the bits of the bitstream, and it obviously doesn't store comments. And what we want to achieve is a partially modularized netlist with annotated bit order information, and you'll see why that is important and what that actually means in a bit. There's 3 stages. The first one we're going to omit here because that's kind of FPGA specific. Then we have the word level structure detection, where we actually try to get the flip-flops, so the storage elements, which each store 1 bit, to organize them in registers of 16, 32 bits, whatever. We have some bigger mux structures, which are basically if branches, kinda. So we want to detect those in like also word level structures, 16-bit, 32-bit, whatever, adders, counters, all kinds of stuff that will help us later on to actually understand what's going on. And then we want to have some form of restoring the bit order, because if you just group flip-flops together, you have no idea in what order these flip-flops make up the register. So first off, the register recovery, basically, that's actually the topic that Nils got invited for this conference for initially, but we decided to do something else then. So this is data flow analysis, which basically uses some metrics to finally recover registers out of the sea of gates. So it basically takes flip-flops, analyzes their control inputs like enable, reset, clock, whatever, and according to these information groups the flip-flops into registers. And that actually allows you to do some cool stuff on its own, like detecting crypto algorithms. If you just look for 128-bit registers, for example, for AES, it can be easily used to just detect crypto in unknown netlists. And that's basically it for Dana. So the outcome of Dana is some, I don't know, 8-bit, 16-bit registers. We do something very similar for muxes. Muxes are just gates that have 3 inputs and 2 data inputs and 1 select input, and the select input basically decides which of the data inputs is forwarded. So you can imagine like these also are heavily used on the data path, so on the kind of logic that works on the actual data of the chip. And here we just look at the select signals and group different flip-flops, different mux gates with similar selects together, and then use some analysis of predecessors and successors to finalize our groupings to like 8-bit, 16-bit mux structures that help us understand the data paths in the end. And then, as I already said, there is adders, there's counters and stuff that we need for address logic, for example, to figure out how addresses are dealt with, that access memory and stuff. So these we identify by structural analysis because they all look the same in the netlist. And then we actually use SMT solving to verify their exact functionality, including resets, enables, whatever. Okay, last but not least, the bit order propagation. As I said, some of the structures lack any information of where which bit or where which flip-flop, where which gate is located within the structure. So we really, like if we do further analysis of the data that passes through these structures, we need to know in what order the bits are. Otherwise it will not make sense. We want to interpret like integers in the end and not bits. So we need to find out how the registers and muxes are organized, how their bit order is. And we take that bit order information from neighboring gates and structures like the adders, for example, that have an inherent bit order through their like carry chains, for example, or the BRAMs, which is just a fixed gate that has like 16-bit inputs in fixed order. So we can take that information and propagate through the netlist to actually recover the bit order. All right, and this is where I hand over to Nils for the fun part.
Okay. Yeah, sorry for so much background information, but now we're gonna do like some cool hardware stuff. So let's have a look at the goal of the third phase again at our starting point. So we basically shifted from like the sea of gates, you know, all these little gates that Julian just showed, to like a sea of modules. So we have like these adders and all these things available, so it's a little more like easier to understand. And now our goal is to figure out what this does on a higher level. And therefore, I mean, you guys know this, when you do like software reverse engineering, you usually try to figure out as much possible as you can on the internet. You look through patents, you look through documentation of your microcontroller and whatnot. So we basically did the same. So we tried to look at the Apple patents that were describing what this was doing. I'm not going into much detail on this one. We also did an analysis of like the communication interfaces. So how does our data actually get into our FPGA? And then in the final thing, we did like the data path understanding to figure out what this actually is doing. So a little bit more background information. So Julian already said that the iPhone, the FPGA in there is not doing, sadly, anything with security, but it's doing like something with the vibration stuff. And it's actually controlling this little thing that you see right over there. This is like the Taptic engine, which basically simulates these nice vibrations that you can feel. And one new addition that the iPhone 7 had was it had like this virtual home button. So there's no physical button anymore. And this thing basically is able to simulate a super realistic click so that you don't actually notice that the real physical button is missing. And as you can imagine, this requires a lot of like signal processing and whatnot. And this is actually what our FPGA was kind of for, to do all of this processing. Okay, so this is some information we kind of derived from the patents and on our own. So basically all of this in the middle, this is like inside the FPGA. So these are the information that we actually reverse engineered ourselves. And everything around that is basically the things you can see on the PCB. So there's like this A10 SoC, which is like the big SoC that Apple designs by themselves, you know, basically a CPU with like a bunch of extra modules on there. And then you have, you know, Maggie talking again to Homer over there, which is, yeah, the thing that basically talks to the motor driver and the Taptic engine in the end. Okay. So we had to get a little bit creative here because it was actually still quite hard figuring out what's happening here because we have no clue about like signal processing. And one thing that we came up with is doing a simulation-based analysis. Yeah? So what does it mean? You can basically do this on partial, yeah, on some selected parts of the netlist where you just like simulate what's going on, which is quite fast and quite nice, and you can like generate some arbitrary inputs on yourself and see what's going on inside. But you can also do like a full netlist simulation. And if you have like a perfectly recovered netlist, that would be super cool because then you could check every signal at any time and see what's like happening there. But we had to get creative on like to feed the chip with the correct data that goes in there. This is quite slow because it's quite big. The netlist has like 10,000 gates and there's like lots of complicated gates inside. So this is like taking a lot longer time. We outsourced it to a server, which was like taking a couple of hours, but it was super cool. So basically the rough idea is the following. So what we wanted to do is we wanted to record the actual data that goes into our FPGA. So basically the communication between the iPhone, PCB, and our Maggie FPGA. So we somehow had to like connect our FPGA to a logic analyzer to record all the input and outputs. Then, as I said, we want to feed the recorded data into a simulator and then simulate what's happening in there. And then we can perform our dynamic netlist behavior. And the cool part is that this allows us to focus on the data path entirely, yeah? Because one of the problems is that with the entire control logic, you have to know what inputs you have to feed to the control logic so that certain actions happen on the data path. But if we have the correct inputs already feeding into our chip, the inputs basically take care of the correct actions on the data path, and this allows us to not reverse engineer these complex state machines and just focus on how the data is processed. Right, so this is kind of what it looks like in hell. I'm going to show you like a little recorded live demo. Over there you have like these waveforms, and if you've ever done like hardware design, you know how painful it's debugging those. Yeah? Imagine how painful it is reverse engineering those. You already see that this is kind of modularized, so there's like some shift registers. We already found like the SPI interface. There's some adders in there, so we could actually do the simulation on the modularized netlist. And it's not super clearly visible in the on the projector here, but all these different nets, so the connection between the gates, have like different colors depending on where that cursor over there is set to. And then this shows you if this certain signal is like 1 or 0 at a certain time. Yeah, and we call that virtual probing because it allows you to access every signal at every given time and observe what it's doing like under operation. So this is what it kind of looked like in hell. Let me just start that video real quick. Okay, so on the right you have like this this waveform viewer, and this basically shows all your clock cycles. Yeah, and you can take that cursor around there, and you can see that these signal changes their color depending on which clock cycle you're on. So basically we know the value of every signal at any time and can use that for a reverse engineering process. Okay, the biggest problem of this was that we were not able to get to the connections of the FPGA, because as you can see here, these things usually have like a ball grid array, so all these connections are underneath the FPGA basically, because it's like soldered on top the PCB, and the I/O is not accessible right away. So we had to be creative, and what we basically did was, we designed a custom breakout board. So we removed m0le from the iPhone PCB, so this is like the idea that we had. We put it on our custom breakout board, soldered that back onto the iPhone PCB, and then as you can see, like with these golden connections on these edges over there, we were able to like basically take all the data out of there and use it to record it with our logic analyzer. So I can show you this was a lot of struggle until we got this working. So basically what we did, step one, we have to remove m0le from the iPhone PCB. Yeah? Problem is we couldn't find a way to remove m0le without destroying it, because there's like some glue on the iPhone PCB that basically prevents it like from catching dust and also like from water or something. So we were never able to get m0le out of there without destroying m0le. So in the end, we just used a mill and got completely rid of m0le. This is kind of what it looks like. Yeah, so there's like this mill that basically just kills m0le. And as you can see now, these connections on the orange circle over there are free for us to use. And what we just did, we bought new parts of m0le, so you can just buy them online. So we just bought a new FPGA, put it on the on our breakout board, which you can see over there. So we put m0le on the breakout board. Then we placed like a cube underneath. You're going to see what I mean by cube in 1 second, to like lift it a bit higher, because there are, like, as you can see, other chips on there, so we needed to get like a bit higher so to actually get it back on the PCB again. So this is kind of what it looks like. So on the PCB, we put like these cubes, which you basically would cut off and then put here. So the finished product you can see over there. So this adds like additional height to it so that it can go back on the board. So another important thing is you had to get like these balls back onto the board, onto the FPGA, and again to our PCB to do the connection. And as you can see, those balls are like super fucking small. So it's like a pain in the ass to do that. Luckily, there are machines that can help you. There's like this reballing machine, and you have like the PCB under the microscope, and you can basically shoot these balls there, and it takes care of you. It takes care of that for you, and in the end, you can see it worked out quite great, and the balls were in the right positions. So that was okay. The problem was we couldn't do that for the iPhone PCB because they never stuck, so we had to do that manually, which was really not fun. So we had to put like another cube on there to actually get it a little bit higher more, because the other parts were too high for us to fit it on again. So in the end, we had like these two cubes, our PCB, and then m0le. This shows basically how we place them on top of each other. That's like a special machine that has like these two cameras that are facing up and down. So on the one part, there's like this breakout board that we put there, and below here you can see the iPhone PCB. And what this camera basically does, it puts like these images on top of each other. So now you can like align them perfectly and then put them down, and then they are like aligned perfectly, and you can solder them back together. Okay, so that was basically it. We got it working in the end, and m0le is now operating like in a normal mode, so that worked out quite great. And we were able to, tap all these connections that are going in and out of m0le and connect them to our logic analyzer to do the analysis and record the inputs. So this is how it looks like. The iPhone, we never put it back in the case, of course. So it's running like this with a stripped functionality, basically. Some more pictures. This is like a on-top view of our setup. And as you can see, the iPhone is actually working, even though, yeah, we did our little magic there. So what lessons did we learn? We had to commemorate 8 iPhones. I think in the end it was even 10 that we destroyed in that process. We ran through Maggie supplies of 2 iPhone repair shops. So this is like, yeah, not a popular part apparently anymore. It took, in the end, we had like a workflow that took about 3 to 4 hours, but figuring out the entire process took us 3 or 4 weeks. And another thing I cannot recommend doing is, once you finished your first iPhone, don't drop it, yeah? So this was the thing after having like these 8 iPhones that were not working. We finally think we got one that was working, and then, yeah, it fell down. So that was not fun. But we eventually got it working. We applied some epoxy so we could like even ship it and transport it, and we had like this nice tower over there that helped us do all of this. So I need to check a bit on the time. I just think we're still good, 36 minutes, great. So what did we do with the recorded data? And I'm going to show you like the first example, and one of the things that the FPGA is basically assisting with is that the processing for the clicks. So in the settings of the iPhone, you can choose how hard you want your haptic feedback to be, like soft, medium, or hard, and you can set like these 3 levels. And now with our setup, we basically recorded what is happening when we set these 3 levels. Yeah? So it's like a super high-level overview. We saw that every time we set like different settings on the iPhone software, that there was like data being sent via this SPI interface to our iPhone. Yeah, so setting it to level 1 issued the sending of this first data package, then setting it to level 2, we observed another data package coming in, and then for level 3 the same. So we had to look at what's happening inside, and this is like a super simplified overview. So in our FPGA, there's like this SPI receiver, and then the data basically goes all up to like some RAMs that are featured in our FPGA. And what we observed basically that the data, once you set them like to the 3 different levels, there's like some curve coming in that we were able to extract using our simulation. Yeah, so we basically observed the content that was in the FPGA after these packages for the levels came in, and we extracted these nice little curves, and you can see like there's like an increased peak, basically, the higher the level is, so the harder the touch should feel. Okay. Yeah, I'm gonna skip through this because I don't have that much time anymore. This is actually like the super complex part, so you're kind of lucky that we cannot get into much detail. So basically what this allowed us to do, and this is like very low level now, there is some DSPs in there that do the computation, and now we had to do like an analysis on, over time on how this all works. In the end, we got a Python module out of it. We basically re-implemented the entire data path from the iPhone in Python. So our Python model that we extracted exactly behaves like the actual data path. So we kind of, we're happy that we moved away from the gates and whatnot to like a higher level of abstraction. And this is where we gave everything, like all the algorithms, all the math formulas that we extracted from out of there. Then in this Python script we gave to our colleague, who has like an idea on how to do signal processing. And after 2 weeks of staring at that, he figured out what this is exactly doing on like a very low level. There's like some Fourier transformations. Don't ask me about this, in there. So it's a very super complex system, and it's actually super cool. Yeah, Apple has like this super weird sensors that even when your iPhone might drop, these little vibrations might have feel a little different. So they have like sensors that, feedback the data into the FPGA to compensate for that, so that it doesn't feel any changed. Okay, so our conclusion is hardware reverse engineering is super painful, but it's feasible even with our limited university resources that we have. So, no idea what's going on behind closed doors at the NSA and whatnot. The dynamic analysis that we used was like for us a key to actually understanding of what is going on in there. And the interplay between like these manual and semi-automated reverse engineering techniques that we came up with and that Julian introduced was actually the key to achieve like this understanding in the end. So what you can basically do is you can do IP theft, so competitor analysis or whatever, and also like maybe, and especially for FPGAs, because they have this updatable bit stream, find meaningful hardware Trojan insertion points, so it poses a realistic threat. Okay, thank you very much.
Any questions? Yeah.
All right, maybe a provocative one first. You've been referring to a restricted budget that you had, which included 8 iPhones being, broken. I just wonder, do you imagine this being ever available for everyday people with everyday budget? You know, it's like they can do some hardware tinkering and get some intelligence out of it like you did?
I mean, for the static part, so basically our tool is open source, it's on GitHub, you can download it and analyze netlists. The dynamic part where we had to capture the inputs, it's probably hard to do without these machines available and without the respective microscopes and stuff. So you need kind of a hardware lab to do the chip off and implementation of the board to capture the inputs. But for the static part, where you just look at the netlist, do some automatic detection techniques, that's completely possible on your machine, on your laptop. That answers your question?
Yeah, to be honest, I was more focused on the hardware part, so I wonder if this will ever be available, you know, for everyday people. What I kind of hear out is that you say no, because you need specialized lab equipment for that, right?
Yeah.
All right, thanks.
But not the very expensive equipment. So that's still affordable to companies, for example, smaller companies or universities, I would say.
We are using FPGAs to accelerate very important functions such as neural networks or AI at the edge of networks. So do you think that this analysis you carried out with the development of the tools and all the stuff related, do you think that this stuff poses some serious threat to the deployment of, for example, AI at the edge of networks?
I have a similar project on machine learning acceleration where we try to manipulate such an accelerator for machine learning networks. But in general, it's not as much of a threat to machine learning, I would say, as it is to security. For example, if you have crypto running on your FPGA and we detect it and we find keys and stuff, that's more serious. For sure, if you can implement hardware Trojans in the accelerators or in the machine learning implementation through hardware reverse engineering, this is of course a threat.
Let's thank again Nils and Julian. Thanks. Sorry for the...
Sure, yeah.